Hello students, in today's class I will teach you about solubility and vapor pressure of liquid solutions as per the syllabus of chemistry for class 12. As you know, we are following the NCERT syllabus rationalized for the year 2023-24. Please note down all the points discussed in this session as the same are very important. I welcome you once again. Solubility. Every solid does not dissolve in a given liquid. While sodium chloride and sugar dissolve readily in water, naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar do not. It is observed that polar solutes dissolve in polar solvents and nonpolar solutes in nonpolar solvents. In general, a solute dissolves in a solvent if the intermolecular interactions are similar in the two, or we may say like dissolves like. Every solid does not dissolve in a given liquid, as I said earlier. Factors which affect solubility are nature of solute, temperature and pressure. Nature of solute, nature of solvent, temperature and pressure. All the four are the factors which affect the solubility of a material or component. First is nature of solute and solvent. Polar solutes dissolve in polar solvents and nonpolar solutes in nonpolar solvents. Thus, like dissolves like. When a solute is added to a solvent, some solute dissolves and its concentration increases. This process is known as dissolution. Some solute particles in solute collide with the solute particles and get separated out of solution. This process is known as crystallization. A stage is reached when two processes occur at the same rate. Under such conditions, the number of solute particles going into the solution will be equal to the solute particles separating out, and a state of dynamic equilibrium is reached. I will explain you about the dynamic equilibrium in the next slide. So therefore, solute plus solvent gives a solution, and this process is reversible. Let it be equation number 10. At this stage, concentration of solute in solution will remain constant under the given condition, that is same temperature and pressure. A solution in which no more solute can be dissolved. Please note, in a solution wherein no more solute can be dissolved at the same temperature and pressure is called saturated solution. Perhaps the concentration can change if we increase the temperature and reduce the pressure, etc. But under the same temperature and pressure, this solution is called saturated solution. An unsaturated solution is one in which more solute can be dissolved at the same temperature. The solution which is in dynamic equilibrium with undissolved solute is the saturated solution and contains the maximum amount of solute dissolved in a given amount of solvent. Thus, the concentration of solute in such a solution is solubility. Thus, we can also call solubility as the concentration of solute in dynamic equilibrium. We'll continue our discussions regarding solubility of a solid in a liquid. As I said earlier, the solubility of a solid in a liquid depends on the nature of solute and solvent, and it also depends on the temperature of the solution. So, the solubility of a liquid is significantly affected by temperature changes. That means if you increase the temperature, the solubility increases. Consider an equilibrium represented by the equation solute plus solvent gives a solution, and this process is reversible. This being a dynamic equilibrium must follow Le Chatelier principle. The dynamic equilibrium means many physical and chemical processes are reversible. A reversible process is said to be in dynamic equilibrium when the forward and reverse process occur at the same rate. Once dynamic equilibrium is established, the concentrations or the partial pressures of all the species involved in the process remain constant. So, this is the explanation for dynamic equilibrium. Thus, being dynamic equilibrium must follow, and this is based on Le Chatelier's principle. In general, if in a saturated solution, the dissolution process is endothermic, that is del sol of H greater than 0, the solubility should increase with rise in temperature. And if it is exothermic, that means the del sol H is less than 0 and the solubility should decrease. These trends are also observed experimentally. So, the fourth factor that affects the solubility of a solution, solubility of a solid in liquid, is the effect of pressure. Pressures does not have any significant effect on solubility of solids and liquids. It is so because solids and liquids are highly incompressible and practically remain unaffected by changes in pressure. Hitherto, we were discussing about solubility of solid in a liquid. Now, we will discuss about solubility of gas in a liquid. Many gases dissolve in water, but oxygen dissolves only to a small extent in the water. It is this dissolved oxygen which sustains all aquatic life. By By aquatic life, we mean the living or growing animals or plants in water. On the other hand, hydrogen chloride gas, that is HCl, is highly soluble in water. Solubility of gases in liquids is greatly affected by pressure and temperature. Please recall, temperature was affecting to a great extent in solubility of solid in a liquid. Pressure was very sparingly affected. But in the case of solubility of a gas in a liquid, pressure and temperature both affect it significantly. The solubility of gases increases with increase in pressure. Consider a system shown in the figure A. That is the left part of the figure shown on your screen. The lower part is solution and the upper part is gaseous system at pressure P and temperature T, capital T. Assume this system to be in the state of equilibrium. That is, the process is reversible and forward and reverse actions are possible. That is, under these conditions, rate of gaseous particles entering and leaving the solution is the same. That is, the rate of entering the liquid and reversible is same. Now, refer to the part B of the figure. Increase the pressure. Here we are putting more pressure and we are trying to compress the gaseous portion part. Now increase the pressure over the solution phase by compressing the gas to a smaller volume. We are reducing the volume here. This will increase the number of gaseous particles per unit volume. That means the gas volume molecules will come closer and closer, and also the rate at which the gaseous particles are striking the surface of solution to enter it, because we have increased the pressure. Thus, the solubility of gas will increase until a new equilibrium is reached, resulting in an increase in pressure of a gas above the solution, and thus its solubility increases. Henry's law. Henry was the first scientist to give a quantitative analysis and relations between pressure and solubility of a gas in a solvent, which is known as Henry's law. Henry's law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of a liquid or a solution. Dalton also concluded that the solubility of a gas in a liquid solution is a function of partial pressure of the gas. Thus, it can be said that the mole fraction represented by the letter X in the solution is proportional to the partial pressure of the gas over the solution. The most commonly used form of Henry's law states that the partial pressure of the gas in vapor phase, that is represented by the symbol small p, is directly proportional to the mole fraction represented by the symbol small x in the solution, may be expressed as P small p is equal to capital K subscript h into x. Here in this equation, small p is the partial pressure, x is the mole fraction, and kh is the Henry's law constant. If we draw a graph between partial pressure and the gas versus mole fraction of the gas in solution, then we will be able to get a plot as shown in the figure. So here the partial pressure is plotted in the y-axis and mole fraction on the x-axis. So this represents the mole fraction x and this represents the p small p partial pressure. In addition, we can also show a table, the relationship between gas temperature, then Henry's constant for different gases like helium, hydrogen, nitrogen, oxygen, etc. etc. Please go through the table. The table may be explained. Here you see helium gas at temperature 293 has a Henry's constant 144.97. Henry constant is at per kilobar. Similarly, hydrogen at 293 degree Kelvin has 69.16. Nitrogen at 293 Kelvin is 76.48. When we increase the temperature of nitrogen to 303, it becomes 88.84. So as we increase the temperature, the Henry's constant also increases. Oxygen at 293 Kelvin has 34.86 and same oxygen at 303 temperature has 46.82 henries per henries per kilobar pressure. So same examples are given for other gases. This is given in the fourth column, fourth, fifth and sixth column. It is obvious from equation 11 above that higher the value of KH at a given pressure, the lower is the solubility of the gas in liquid. Thus, it can be seen also from table 2, this is table 2, that KH value for both nitrogen and oxygen increase with increase in temperature, indicating that, please underline, the solubility of gases increases with decrease in temperature. So the solubility of gases increases with decrease in temperature. See, it was for nitrogen it was 88, solubility was 88, so it decreased to 76. It is due to this reason that aquatic species are more comfortable in cold water rather than in warm water. So temperature decrease means they are comfortable. Henry's law finds several applications in industry and explains some biological phenomena. Notable among these are listed below. Soft drinks and soda water bottles. To increase the solubility of carbon dioxide in soft drinks and soda water, the bottle is sealed under high pressure. This is one of the industrial applications. The next one is the scuba tanks used by scuba divers. Scuba divers must cope up with high concentration of dissolved gases while breathing air at high pressure under water. Increased pressure increases the solubility of atmospheric gases in the blood. When the divers come towards surface, the pressure gradually decreases. This releases the dissolved gases and leads to the formation of bubbles of nitrogen in the blood. Thus, this will result in blockage of capillaries and creates a medical condition known as bends, which are painfully and dangerous to the life. To avoid bends as well as the toxic effect of high concentration of nitrogen in the blood, the tanks used by scuba divers are filled with air diluted with helium, that is 11.7% of helium and 56.2% of nitrogen and 32.1% of oxygen. Similarly, the another case is that of the trekkers. At high altitudes of partial pressure of oxygen is less than that at the ground level. This leads to low concentrations of oxygen in the blood and tissues of people living at high altitudes or mountain climbers. Low blood oxygen causes climbers to become weak and unable to think clearly, symptoms of a condition known as anoxia. Now, having studied about the principles of solubility in brief, let us work out some numerical example. Example number 1. If now nitrogen gas is bubbled through water at 293 Kelvin, how many millimoles of nitrogen gas would dissolve in 1 liter of water. Assume that nitrogen exerts a partial pressure of 0.987 bar. Given that Henry's law constant for nitrogen at 293 Kelvin is 76.48 kilobar. Please read the question once again and I will go ahead with the solution. The solubility of gas is related to mole fraction in aqueous solution is given by the Henry's law. Therefore, mole fraction of nitrogen is equal to partial pressure of nitrogen divided by Henry constant. So, it is given the partial pressure as 0.987 bar here in the question divided by the Henry constant for nitrogen is also given in the question. So, it is 76.48 kilobar or 76,000 converting into bars 76,480 bars. That simplifying becomes 1.29 into 10 to the power of minus 5. As 1 liter of water contains 55.5 moles mole of it, therefore N represents the number of moles of nitrogen in solution. Therefore, X of nitrogen will be equal to N mole divided by N mole plus 55.5 moles of water equals N divided by 55.5 because N moles of hydrogen is very negligent, small, hence N mole can be neglected. It becomes N by 55.5. That simplifying we get 1.29 into 10 to the power of minus 5. Thus, N is equal to 1.9 into 10 to the power of minus 5 into 55.5 mole. That is equal to, that is cross multiplying. N on the left side retain and this you cross multiply here. And that becomes 7.16 into 10 to the power of minus 4 mole. Therefore, 7.6 into 10 to the power minus mole into 1000 mole divided by 1 mole is equal to 0.716 millimole. That is 1000 becomes 10 to the power of minus 3. The next topic is vapor pressure of liquids. Liquid solutions are formed when solvent is a liquid. The solute can be a gas, a liquid, or a solid. Solutions of gases in liquids have already been discussed in previous sections. In this section, we shall discuss the solution of liquids and solids in a liquid. Such solutions may contain one or more volatile components. Generally, the liquid solvent is volatile. The solute may or may not be volatile. We shall discuss the properties of only binary solution, that is, the solutions containing two components, namely the solutions of liquid in liquids and solids in liquids. So, let us move to the subsection. Vapor pressure of liquid liquid solutions. Consider a binary solution of two volatile liquids. I denote them as 1 and 2. When taken in a closed vessel, both the components would evaporate. And eventually, an equilibrium would be established between the vapor phase and the liquid phase. Let the total vapor pressure at this stage be P total and P1 and P2 be the partial vapors of the two components 1 and 2 respectively. These partial pressures are related to mole fractions x1 and x2 of the two components 1 and 2 respectively. Now Raoult's law. The French chemist Francois Martin Raoult, who lived in 1886, gave the quantitative relationship between them. The relationship is known as Raoult's law, which states that for a solution of volatile liquids, the partial vapor pressure of each component of solution is directly proportional to its mole fraction present in the solution. So let us write and let us state once again. The Raoult's law states that a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. Thus, for component 1, P1 is directly proportional to X1. That is, the X1 is the mole fraction of the component 1. And P1 equals P1 to the power of 0 X0, X1. That let it be equation 12. Where P10 is the vapor pressure of the pure component 1 at the same temperature. Similarly, the vapor pressure of pure component 2 is given by the relation P2 is equal to P2 naught into X2. Let it be equation 13. So I will repeat. For P1 component 1, P1 is equal to P1 naught X1, and for the second component P2 equals P2 to the P2 naught into X2. This is as per Raoult's law. According to Dalton's law of partial pressures, the total pressure P over the solution phase in the container will be the sum of partial pressures of the component of the solution as given below. That is, P total will be equal to P1 plus P2. Let it be equation 14. Substituting the values of P1 and P2, we get P total equals P1 plus P2, that is equal to P1 naught X1 plus P2 naught X2. That is equal to, taking P1 naught common, we get 1 minus P1 naught plus X2 P naught. Following conclusions can be drawn from vapor pressure of liquid to liquid solutions. Let us summarize the conclusions from the equation 116. So a plot of equation 16, that is P total equals P1 naught plus P2 naught minus P1 naught into X2 is shown on the screen. This plot of vapor pressure and mole function of an ideal solution at constant temperature. So here, you please see here, the ideal solutions are x1 equal to 0. X1 is equal to 1 on the left hand side, x2 equal to 0 on the extreme right hand side. Similarly, for the component 2, the mole fraction x2 equal to 0 is at the origin, and on the extreme end, that is right hand side, x2 is equal to 1 here on the x-axis. Here the x-axis is x2 and it is the mole fraction. The vapor pressure of the two components are shown in the vertical axis. Here. The dashed line here, this is the for component 1 and this is for component 2 is also plotted. It represents the partial pressure of the components. It can be seen from the plot that P1 and P2 are directly proportional to X1 and X2 respectively. The total vapor pressure is given by the lines marked 3 in the figure. So here this dark thick line shows the total pressure P1 plus P2, which represents the equation 16 shown on the screen. These are the partial vapor pressures of pure components. So let us summarize our conclusion, draw conclusion. The total vapor pressure over the solution can be related to mole fraction of any one component. So X6 can be either X2 of second component or even X1 of the first component. The total vapor pressure over the solution varies linearly with mole fractions of component here on the screen. Depending on the vapor pressures of pure components 1 and 2, the total vapor pressure over the solution decreases or increases with the increase of mole fraction of component 1. The composition of vapor phase in equilibrium with solution is determined by the partial pressures of the component. If Y1 and Y2 are mole fractions of components 1 and 2 respectively, in the vapor phase. So this Y1 and Y2 are mole fractions of components 1 and 2 in vapor phase. And using Dalton's law of partial pressure, we can write the equation. P1 is equal to Y1 P total. Let it be equation 17. Similarly, for partial pressure P2, we can write P2 is equal to Y2 into P total. Let it be equation 18. In general, we can write Pi is equal to Yi into P total. You remember these equations. Let it be equation 19. Let us understand the concepts of vapor pressure liquid to liquid solution by solving a numerical example. So question number 2 appears on your screen. Vapor pressure of chloroform, whose formula is CHCl3, and dichloromethane, whose formula is CH2Cl2, at temperatures 298 Kelvin or 200 mmHg and 400 mmHg respectively. First question is calculate the vapor pressure, that is P total, of solution prepared by mixing 25.5 grams of CHCl3 and 40 grams of CHCl2 at the temperature 298 Kelvin. The second part of the question is calculate the mole fractions of each component in vapor phase. So please read the question once again, and I will proceed with the solution and note down the important points. First question we will solve. Here they have asked we have to calculate the P total, that is total pressure. So first one is molar mass of CHCl2 is given by, there is a carbon atom whose mass is 12. 12 into 1 carbon atom plus H2 is 2. So 2 into 1. 2 molecules of carbon with molecular weight 1 plus molecular weight of chlorine is 35.5. There are 2 molecules into 2. So that is 85 grams per mole. Next step, we will calculate the molar mass of the second component, that is CH2Cl2. That is given by carbon is 12 into 1, hydrogen is single atom 1 into 1, and chlorine is 35.5 into 3, and that total simplifying it comes to 119.5 grams per mole. Therefore, moles of CH2Cl2 equals, here in the first case, 40 grams divided by 85. This 40 grams is given in the question. 40 grams of CHCl2. So 40 grams by 85 grams per mole. This becomes 0.47 mole. Next we will calculate the moles of CHCl3. So it is 25.5, it is given in the question, divided by 119.5 grams per mole, that is equal to 0.213 moles. Hence the total number of moles will be equal to 0.47 plus 0.213, that is equal to 0.683 mole. Now we will calculate the molar fraction. X of CH2Cl2, that is given by 0.47 divided by 0.683, that is equal to 0.688. Similarly, for CHCl3, X of CHCl3 is equal to 1. Total solution is 1. So minus this 0.68 gives the molar fraction of CHCl3, that is equal to 1 minus 0.688, that is equal to 0.312. Using the equation, P total is equal to P1 naught plus P2 minus P1 naught, P2 naught minus P1 naught into X2. Here, this is the total pressure, this is the partial pressure P1 of component 1, and P2 is the partial pressure of component 2. So that becomes, substituting, it is 200. P1 naught is 200 plus 415 minus 200 into 0.688, that is x2, value of x2. P2 is given as 415 pressure, and minus 200 is the pressure of CHCl2, CH2Cl2. That becomes 200 plus, simplifying this, 147.9, that is equal to 347.9 millimeters of Hg, mercury. That is the answer for first part, that is we have calculated. Next step, we will calculate the value of partial molar fraction. Using the equation 19 in the previous sheet, that is, the equation 19 is Pi is equal to Yi into P total. Pi is equal to Yi into P total, and it is again rearranging, we get Yi is equal to Pi divided by P total. So we have to calculate the mole fraction of the component in gas phase Yi. Therefore, P of CH2Cl2 is equal to 0.688 into 415 millimeters of mercury, that is equal to 285.5 millimeters of mercury. P of CHCl3 is equal to 0.312 into 200 mm mercury, that is equal to 62.4 millimeters of mercury. Therefore, Y of CH2Cl2 is equal to 285.5 mm of mercury divided by 347.9. that is the value of P total, that is equal to 0.82. So Y of CH2Cl3 will be 62.4 mm of Hg divided by 347.9 millimeters of mercury. Its value simplify, it becomes 0.18. So there is one small note. We have to know that since CH2Cl2 is a more volatile component than CHCl3, because P of CH2Cl2 not equal to 415 Hg and P of CH3Cl3 not is equal to 200 mm, it is given, and vapor phase is also richer in CH2Cl2. That is equal to Y is equal to 0.82 and Y of CHCl3 is equal to 0.18. It may thus be concluded that at equilibrium, vapor phase will be always rich in the component which is more volatile. So, in this case, CH2Cl2 is more volatile. Hence, the equilibrium vapor phase will always be rich in component of CH2Cl2. Raoult's law as a special case of Henry's law. According to Raoult's law, the vapor pressure of a volatile component in a given solution is given by Pi is equal to Xi into Pi naught. That is from equation 19. In the solution of gas in a liquid, one component is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry's law, which states that P is equal to Kh into X, where P is a partial pressure, Kh is Henry's constant, and X is the mole fraction. If we compare equations of Raoult's law and Henry's law, it can be seen that partial pressures of volatile component or gas is directly proportional to its mole fraction in solution. Only proportionality constant Kh differs from P1 naught. Thus, Raoult's law becomes a special case of Henry's law in which Kh is equal to P1 naught. Vapor pressure of solutions of solids in liquids. An important class of solutions consists of solids dissolved in liquids. For example, sodium chloride, glucose, urea, and cane sugar in water, or another solution is iodine and sulfur dissolved in carbon disulfide. Some physical properties like vapor pressure of these solutions are quite different from those of the pure solvent. Liquids at a given temperature vaporize, and under equilibrium condition, the pressure exerted by the vapors of the liquids over the liquid phase is called the vapor pressure. So what is vapor pressure? So this is due to liquids at a given temperature, vaporization of liquids at a given temperature, and under equilibrium condition, the pressure exerted by the vapors of liquid over the liquid phase is called vapor pressure. And this vapor pressure is shown in figure A on the screen. This is the creation of vapor pressure due to liquids. The vapor pressure of solution is solely from the solvent alone. So this is due to pure solvent. This vapor pressure is due to pure solvent. The vapor pressure of a solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. So here the figure B also, there is a vapor pressure, but vapor pressure due to solution is always lower than the vapor pressure of the pure solvent. In the solution, the surface has both solute and solvent molecule. In this surface here, it has got both solute and solvent. The green color is due to solvent and the black colored molecules are due to solute. Thereby, the fraction of surface covered by the solvent molecule gets reduced. Consequently, the number of solvent molecules escaping from the surface is accordingly reduced. Here it becomes cramped and it tries to limit the escape of molecules from here. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced. Thus, the vapor pressure is also reduced. Hence, Ps is less than P0. This is called lowering of vapor pressure. That is equal to the difference between the two is given by the relation delta P is equal to P0 minus Ps, where delta P equals lowering of pressure and P0 is vapor pressure of pure liquid, here solvent as shown in figure A, and Ps is the vapor pressure of solution, solute and solvent. In a pure liquid, entire surface is occupied by molecules of the liquid. If a non-volatile solute is added to solvent to give a solution, as shown in figure B, the vapor pressure of the solution is solely from solvent alone. This vapor pressure, here in the case B, of the solution at a given temperature is found to be lower than the vapor pressure of pure solvent at the same temperature. In the solution, the surface has both solute and solvent molecules. Thereby, the fraction of surface covered by solvent molecules get reduced. The surface gets reduced. Consequently, the number of solvent molecules escaping from surface is correspondingly reduced. Thus, the vapor pressure is also reduced. The decrease in vapor pressure of solvent depends on the quantity of non-volatile solute. So, it is the function of quantity, not the quality. Quantity of non-volatile solute present in the solution, irrespective of its nature. For example, the decrease in vapor pressure of water by adding 1 mole of sucrose to 1 kg of water is nearly similar to that produced by adding 1 mole of urea to the same quantity of water at same temperature. Raoult's law for solution of non-volatile solute. Raoult's law in its general form can be stated as, for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. Let me write it on the slide. Raoult's law in general form states that for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. In a binary solution, let us take or denote the solvent by 1 and solute by 2. When solute is non-volatile, only the solvent molecules are present in the vapor phase and contribute to the vapor pressure. Let P1 be the vapor pressure of component X1, that is X1 is mole fraction, and P1 not be the vapor pressure in the pure state. This is the pure state. Then according to Raoult's law, P1 is proportional to X1. P1 is the partial pressure and X1 is the mole fraction. So P1 is equal to X1 P1 naught. Let it be equation 20. This proportional constant is equal to the vapor pressure of the pure solvent P1 naught. That is P1 naught. So a plot between the vapor pressure and mole fraction of solvent is linear as shown in the figure. So here if we plot mole fraction X along the x-axis and vapor pressure along the y-axis, then the graph is a linear, is a straight line inclined at some angle. So it is vapor pressure of pure solvent is here. Now we will answer some of the multiple choice questions. In this section, four options are given. Question is asked and then four options are given. You have to choose the correct answer or the nearest equivalent answer which satisfies the question. So let us start. Identify and choose the factors on which the solubility depends. First one is nature of solute, nature of solvent. Third one is temperature and pressure. So four options are given. So these choices here, the factors are given number 1, number 2, number 3 and number 4. And you have to choose the combination which are all responsible for the solubility of the solution. So four options are given. Option A only 1, 2, 3. Option B 1, 3 and 4. Option C only 1 and 4. And option D 1, 2, 3 and 4. So you have to identify the correct answer. Okay. Let us think over and mark the correct answer. Now you have to apply your mind and mark the correct answer. Correct answer is D. Next question. H2S is a toxic acid used in qualitative analysis. If solubility of H2S in water at STP is 0.195 m, what is the value of KH? So, four different choices are given. A 0.0263, B 69.16 bar, etc. etc. Now you have to make some calculations and mark the correct answer. So let us analyze. Number of moles of H2S is given as 0.195. Number of moles of H2O is 1000 divided by 18. That is equal to 55.55 mole. Mole fraction of H2S will be equal to 0.195 divided by 0.195 plus 55.55. That is equal to 0.0035. So pressure at STP is 0.987 bar. According to Henry's law, P, the pressure is equal to KH into X, or KH is equal to P divided by X, that is equal to 0.987 divided by 0.0035, that equal to 282 bars. This answer is given as option D. Please mark it. Next question. Partial pressure of a solution component is directly proportional to its mole fraction. This is known as, four options are given: Henry's law, Raoult's law, distribution law, or Ostwald's dilution law. So the question is partial pressure is directly proportional to mole fraction. So this is given. You have to remember and mark the answer as the B because the pressure and mole fractions are related in Raoult's law. Question number 4. Among the following substances, the lowest vapor pressure is exerted by water, ether, alcohol, and mercury. You have to analyze and answer correctly. So mercury is non-volatile. So answer D is the correct answer. Next question. Question number 5. 5 ml of 1N HCl and 20 ml of N by 2 H2SO4 and 30 ml of N by 3 HNO3 are mixed together and volume made to 1 liter. The normality of the solution is given by N by 5, N by 10, N by 20 and N by 40. So you have to analyze. So N1 V1 plus N2 V2 is equal to N4 V4. That is equal to 1 into 5 plus half into 20 plus 1 by 3 into 30 equals N4 into 1000. Simplifying, we get N4 as 1 by 40, N by 40. So D is the correct answer. Please mark it. Next question. Which of the following is dependent on temperature? So molarity, option A is molarity, mole fraction, option C is weight percentage and molality. So which one is dependent on temperature? So it is, you have to analyze and remember and mark A as the correct answer. A solution of sodium sulfate contains 92 grams of sodium plus Na plus ions per kg of water. The molality of Na plus ions in that solution in mole per kg is option A 8, option B 4, option C 12 and option D 16. Please analyze and calculate. Molality M, small m represented by small m is 92 grams. It is given divided by 23 grams into 1000 grams per kg divided by 1000. That is equal to 4. So the correct answer is B, option B, that is 4. Please mark it. Question number 8. If molality of dilute solution is doubled, the value of molal depression constant Kf will be A halved, B tripled, C unchanged and D is doubled. So analyze and mark the correct answer. The value of molar depression constant Kf is constant for a particular solvent. Thus, it will be unchanged when molality of dilute solution is doubled. So option C is the correct answer. Please mark it. Next question. We'll continue with multiple choice questions. Question number 9. Which part of the following is useful in relating concentration of solution with its vapor? Mole fraction. Option A is mole fraction, option B is parts per million, option C is mass percentage and option D is molality. You have to interpret, remember and mark. So option A is the correct answer. Next question. On dissolving sugar in water at room temperature, the solution feels cool to touch. Under which of the following cases dissolution of sugar will be most rapid? Underline most rapid, where the rapidity is more. So four options are there: sugar crystals in cold water, sugar crystals in hot water, powdered sugar in cold water, and option D is powdered sugar in hot water. You please interpret and remember and mark it. Powdered sugar has large surface area, hence it dissolves faster in hot water. This option is available as option D. Please mark it. Next question. 4 liters of 0.2 m, capital M, aqueous solution of NaCl was diluted by adding 1 liter of water. The molality of the resultant solution is, four options have been given: A 0.004 m small m, 0.008 m, 0.012 m, and 0.016 m. So you have to calculate and mark it. Calculations are shown on the screen. M1 V1 is equal to M2 V2. That is 0.02 m into 4 liter. 4 liter is V1, that is equal to M2 into 5L. That is equal to M2 into 0.02 into 4 divided by 5, and its value is 0.016 m. So you please mark it. Next question. Value of Henry's constant Kh is, Kh increases with increase in temperature. Option B decreases with increase in temperature. Option C remains constant, and D first increases then decreases. So you have to identify the correct answer and remember and mark the correct answer. The correct answer is option A. With this, we come to the end of section 1.4, that is vapor pressure of liquid solutions. In the next session, we will discuss 1.5, that is ideal and non-ideal solutions, colligative properties, and determination of molar mass. Till then, goodbye.